Energy comes in many forms, but the basic definition is in terms of work. In physics, work and energy have special meanings. Work is the product force of F, exerted on an object times the magnitude of the displacement S. Work is done when a force F moves the body through a distance S. Work equals force times distance. Interestingly, even if a force is applied, if there is no displacement, no work is done. Now let's try it. Say a frictionless box is at rest on a table, 0.10 meters away from the edge. How much work is done on by the box when a person applies a force of 100 newtons until the box reaches the end of the table? Use the equation for work to find the answer. Plug in the force of 100 newtons and the distance of 0.10 meters, and you'll find that the work exerted was 10 joules. Now this equation only works when the force and the displacement are in the same direction. If they are in different directions, you need to account for the angle in your equation. Therefore, work equals force times the distance is now work equals force cosine theta times the distance. Let's do another problem. You have the same box at rest on a table 0.10 meters away from the edge. This time, you attach a rope to one end and pull the box from a 25-degree angle above the horizontal, with the same force of 100 newtons. Plug in all the variables to the equation, and you find that the work exerted was 9.06 joules. Now you may be wondering why I put a J after I find the work. I'll tell you why. The unit of work is the Newton meter. This makes sense because the unit for force is the Newton and the unit for distance is the meter. The product of these two equals work. The Newton meter was given the name the joule after James Joule, who played a big role in figuring out the concepts of work and energy. Now let's talk a little bit about energy. You do work in order to throw a ball and get it moving. After you have exerted work, the ball has acquired energy. We will be talking about two different types of energy, kinetic and potential. Kinetic energy is the energy of motion. After a simple derivation of the equation for kinetic energy, it is Ke, kinetic energy, equals 1/2 mass times velocity squared. In order to account for a change in kinetic energy, delta Ke equals 1/2 mv squared final minus 1/2 mv squared initial. Here's a question using kinetic energy. Determine the kinetic energy of a 625 kilogram roller coaster car that is moving with a speed of 18.3 meters per second. Plug in the variables into the equation for kinetic energy. Multiply, and now you have the answer. 1.05 times 10 to the 5th joules. Potential energy is the stored energy in an object due to its position or configuration. The equation is Pe, potential energy, equals mass times gravity times height. Lifting an object adds energy because of where the object is in Earth's gravitational field. If you were to change its position, such as lifting the object, you would be changing its height. In order to account for a change in position, use mass times gravity times the change in height. Let's try a quick problem. You want to put your 2 kilogram textbook back on its shelf. You lift the book at a constant speed from the floor to a height of 3 meters. What is the work done by you? Since there is a change in height, make sure to include that in your equation. Plug in the numbers to the equation, and you should get 58.8 joules. We can use both of these types of energies together to solve problems. This is through the concept of the conservation of mechanical energy. The concept states that energy is neither created nor destroyed. However, energy can be converted from kinetic to potential and vice versa, but total energy is conserved. If no external non-conservative forces act, the total mechanical energy of the system is a constant. By using the equation at the bottom, we can solve more dynamic problems. Let's try it. A car is coasting as it approaches the bottom of a hill at a speed of 10 meters per second. The hill is 4 meters high. The car is able to make it over the hill without applying more gas. Find the speed at which the car crests the hill, ignoring air resistance and friction. Now use the new equation. Since there is no initial potential energy due to the car being at the lowest point, you can cross out the initial potential energy. Now write out the equation. You are able to divide out the mass because the mass is a constant and does not affect the outcome. Now use algebra to solve the equation for the variable of final velocity. Plug in the numbers and you should get an answer of 4.65 meters per second at the crest of the hill. The total energy of a system does not change. However, energy may be converted into other forms, such as heat and sound. If you were to drop a bowling ball to the floor, some energy will be converted into sound. Some will be converted into the distorting of the floor or even the ball, and some will be converted into heat. The ball and the floor will be slightly warmer after the collision, but energy is always conserved. The last idea I am talking about is power, the average rate at which work is done. It is obtained by dividing work by the time required to perform the work. P, power, equals work over time in seconds. The unit of power is joules per second, which has been given the name of the watt. Since there are 745.7 watts in 1 horsepower, to convert watts to horsepower, divide your amount of watts by 745.7. If you have done 300 joules of work in 1 second, how much power do you have? Plug into the equation and you get 300 watts. To find horsepower, divide by 745.7 and you should get an answer of 0.402. Well, that's it for this little overview of work and energy. Now you can see how much work and energy play into the world around us. Hope this video is helpful. Thanks for watching.